Lecture 9 covers Section 3.4. At the end of today's lecture, you should be able to formulate an expression for work for moving boundary systems, as well as calculate and apply the Polytropic Index for the formulation of work to moving boundary systems. Let us begin by considering a moving boundary system. A moving boundary system is where our control surface is able to move, such as a piston cylinder or compressor. Let us consider a piston cylinder below, in which the cylinder is raised a distance of dl from state 1 to state 2. That is, the volume contained within our piston cylinder is initially V1 and then it increases to V2 as our piston is raised. Now, if we consider this as a quasi-equilibrium process, we can calculate the work done onto or by the system. By definition of work, delta W is equal to F dx. Our force is pressure times area, and our change in distance is dl. Therefore, delta W is equal to our pressure times the area of our piston times our change of length, and our area times our change of length is our change of volume, dV. Therefore, work going from state 1 to state 2 is equal to the integral from state 1 to state 2 of delta W, which is equal to the integral from state 1 to state 2 of P of E dV, where our pressure can vary as a function of volume. Now, recalling integration is calculating the area underneath the curve, we can have various descriptions of our work done. That is, as the piston moves between our two states, P can have a varied dependence on our volume. That is, work is path dependent. And recall we use the inexact differential delta W, since W is a path function. And we will use our exact differential dV when V only depends upon our initial and final states. Now, to quantify the path dependence of work, we must consider a polytropic process. A polytropic process is a process pertaining to a function which has different values for one variable. And our polytropic process is defined as P v to the n is equal to a constant, where n is our polytropic index. N is a real number bounded between negative infinity and positive infinity. Now, our ideal gas law is considered a polytropic process. PV is equal to MRT. That is, P v to n is equal to MRT, a constant on our right-hand side. As mentioned, our polytropic index is bounded between negative and positive infinity. However, there are four unique n's we are going to consider. When n is equal to 0, we have an isobaric process. When n is equal to 1, we have an isothermal process. When n is equal to gamma, we have an isentropic process. And when n is equal to infinity, we have an isochloric process. Now, our polytropic index can be visualized in the following link on a PV diagram, and we see that n is bounded between negative and positive infinity. N can exist as a negative number. Now, when n is equal to 0, let's look at our polytropic process equation. PV to the n is equal to constant, or P v to the 0th power is equal to constant. V to the 0th power is equal to unity, which means our pressure is a constant. When n is equal to infinity, P v to the infinity is equal to a constant. The only way for this equation to be satisfied is if V is a constant. So, you may wonder, why is this useful? Well, given any value for a polytropic index, we can calculate work considering its path dependence, and we will formulate how to calculate n given our pressure and volume. Now, let us construct an equation for work based upon our polytropic index. Recall work from state 1 to state 2 is equal to integral from state 1 to 2 of delta W. Or this is equal to integral from state 1 to 2 of our pressure, which is a function of volume, with respect to our change of volume. Now, based upon our definition of our polytropic process, P v to the n is equal to constant, which means P1 v1 to the n is equal to P2 v to the n, which are all equal to a constant. If we rearrange this expression for pressure, pressure is equal to P1 v1 to the n over v to n, which is also equal to P2 v2 to the n per v to the n, which is also equal to a constant, per v to the n. Now, if we reinsert this expression for pressure within our expression for work, we'd have work from state 1 to state 2 is equal to integral from state 1 to state 2 of P dV, which is equal to a constant times the integral from state 1 to state 2 of 1 per v to n dV. Our integrand 1 per v to the n can be expressed as v to the minus n. Now, if we insert this back into our expression for the integral of work, we can see our work from state 1 to state 2 would be equal to a constant times the integral from state 1 to state 2 of v to minus n dv, which is equal to constant per 1 minus n, v to the 1 minus n, evaluated between states 2 and 1. If we evaluate this, we'd have our work from state 1 to state 2 is equal to a constant per 1 minus n times the quantity v2 to the 1 minus n minus v1 to the 1 minus n. Now, recalling our definition of our polytropic process, we can substitute in the respective values for our constant. That is, our work from state 1 to state 2 can be expressed as c per 1 minus n times v2 to the 1 minus n minus c per 1 minus n times v1 to the 1 minus n. Or we'd have p2 v2 to the n v2 to the 1 minus n minus p1 v1 to the n v1 to the 1 minus n per 1 minus n. And recalling x to the n times x to 1 minus n, our exponents add, which just gives us x, we're left with an expression for work based upon our pressures and volumes of states 1 and 2 and our polytropic index. That is, our expression for work going from state 1 to state 2 is equal to P2 V2 less P1 V1 per 1 minus n. Now note this is dependent upon our pressure and volume at our initial and final state and our polytropic index, n, which we have to calculate. Now you may be wondering what happens when n, our polytropic index, is equal to unity, i.e. we have an isothermal system. Well, we have to rederive a separate work expression. That is, when we take the limiting case of n is equal to 1, our polytropic expression becomes Pv to n is equal to constant, which is equal to P1 V1. If we rearrange for P, we have P is equal to P1 V1 per V to n, which is equal to P1 V1 per V. If we substitute in P within our definition of work, we'd have our work from state 1 to state 2 is equal to integral from state 1 to state 2 of P dV, which is equal to P1 V1 times the integral from state 1 to state 2 of 1 per V dV. Now we note that P1 and V1 are constants. That is, we are not integrating with respect to V1, rather we're integrating with respect to V. Thus, our work from state 1 to state 2 would be equal to P1 V1 times the natural log of V evaluated between state 2 and state 1, which is equal to P1 V1 times the natural log of V2 per V1.